a number of different ways of measuring the charge on proteins. You can use the Donnan effect, or you can use titration. Both of these require large quantities of material, and they both make an assumption about ion binding. You have to go back and measure, for example, in the Donnan effect, you have to measure the displacement of other ions across the membrane to make sure that the charge that you're calculating based on the Donnan effect is the correct charge. In general, the most general way of measuring charge is using electrophoresis. There are 3 different kinds of devices that are available. They all have advantages and disadvantages. The one, to my mind, is the very best is the membrane confined electrophoresis. It is the most accurate and requires the smallest volume of material. In all these electrophoretic devices, what you're doing is putting a charged molecule in an electric field. If we balance the forces on there, we have the force of the charge on the molecule times the electric field, and there's a frictional force which is going to be pointing in the opposite direction. Those two are going to balance, leading to a constant velocity. Complicating this is the fact that the electric field is distorted, since the protein does not allow the electric field to penetrate it. It has to go around it. And also complicating it is the fact that the solvent is moving in the opposite direction simultaneously. So we have to deal with the fact that the ion is being affected by the solvent as well. If we balance those two forces and take into account that the electric field is the electric current divided by the conductance in the cross-sectional area, we get the equations that we saw before. That is, the electrophoretic mobility is the effective charge divided by the frictional coefficient. And we can adjust that effective charge for the solvent effects to get the Debye-Huckel-Henry charge. Now there's some interesting facts. This is the person that's shown here is Arne Tiselius, won the Nobel Prize in 1947 for his work on electrophoresis, and he was interested in measuring the charge on proteins and other biological molecules. But there's some interesting facts to keep in mind. You don't really move the charge object in the solution. You move a neutral object. The explanation for this is a little bit involved and not something we'll go into today unless someone wants to know more about that later. What complicates the charge determination is that the protein itself is contributing to the field. The electric field is shown on the right as the electrical current I divided by the conductance kappa in the cross-sectional area. And both the current and the conductance are going to be affected by the presence of the macromolecule, because it's carrying a part of the current, it's carrying some of the charge contributing to the current. There's the momentum transfer from the solvent, and a problem that plagues electrophoretic measurements a lot is thermal convection. So the 3 answers that Arne Tiselius came up with is use a gel support, so acrylamide gels or agarose gels, reduce the cross-sectional area, which is capillary electrophoresis, or he can work at a temperature around 4 degrees. And he did a considerable amount of work on this and showed that you're going to get convection in your system if the power dissipation exceeds 10 milliwatts per centimeter. And this can become a problem in electrophoretic light scattering, giving rise to results that are inconsistent. So there's some good practices that also come from this. The first one is that you want to have sufficient salt in your system that your macromolecule is not carrying a significant fraction of the current. What we've found working in my laboratory is you need to have a minimum of 10 millimolar salt. If you go below that, you start seeing distortions in the charge determinations because the macromolecule is now affecting the electric field and its electrophoretic mobility is not exactly what you would calculate it to be. You have to go to a higher salt, actually, if you have a high concentration of protein. So if you're working at concentrations of 10 mg per mil or 20 mg per mil protein, you need to have a higher salt concentration, or if you have a molecule that has a high charge on it. We're doing some work right now with some proteins that have charges of 80. And in that case, we can't work at 10 millimolar. We have to work at 20 millimolar in order to get reliable results. If you work at either extreme of pH, either pH is below 4 or pH is greater than 10, protons and hydroxyl will contribute significantly to the electric current because they have such a high electrophoretic mobility. They can move 100 times faster than something like a sodium ion. And as a consequence, you again need to have a higher salt concentration under these conditions in order to get an accurate charge determination. So the recommendation we've come up with and again, we've been working on this for almost 25 years, is that you have a 100 millimolar electrolyte, either potassium chloride or sodium chloride, and 10 millimolar of whatever buffer you want to use, phosphate, tris, bistress, propane, acetate. The only rule with the membrane-confined electrophoresis is you cannot use polycarboxylic acid buffers such as citrate or succinate, but acetate works just fine. If you use 10 millimolar buffer and 100 millimolar KCl, the charge that you determine, the Debye-Huckel-Henry charge, is going to be very close to the actual charge on the protein. Now, if you want to ask what the charge on the protein is at a low salt concentration, say just 10 millimolar histidine, what you do is you make measurements at 2 or 3 salt concentrations, 100 millimolar, you want to go a little bit higher, you go to 150, down to 50, 20, 10, and extrapolate the charge back to zero added salt. And what you'll find when you do that, again, is the charge typically the Debye-Huckel-Henry charge in particular, does not change more than about 10 to 15%. So there are lots of ways of measuring the charge. Capillary electrophoresis requires very little material. It is extremely difficult, especially with a new protein, because you have to find conditions where the protein doesn't stick to the capillary wall. Electrophoretic light scattering is the only technique that provides both the electrophoretic mobility and the Stokes radius simultaneously, but it has problems with precision, as you'll see in a minute. Membrane-confined electrophoresis requires only a small quantity of material. It's fairly rapid. It's accurate. It gives you a very direct measure of the electrophoretic mobility. You can actually see the material moving in the cuvette. The only disadvantage to it is that you can't use polycarboxylic acids in your solvent. There's a second type of technique for measuring charge in the membrane-confined electrophoresis. It's called steady-state electrophoresis. It is the analog of sedimentation equilibrium. It is by far the most accurate way of determining charge. You can trace the equations for it through non-equilibrium thermodynamics. The only disadvantage to it is that it's quite slow. It takes many hours, 10, 15 hours per electric field to get a charge measurement. When we compare these different methods, this is work that we're doing in BITSE right now, looking at the serum albumin and 10 millimolar sodium chloride, 10 millimolar tris. So we're looking at low salt. This is so we can compare data that were required by titration, by Tanford. There's some other data using electrophoresis that were data required in the 1980s. The calculated values that I'm not sure what color that is, strange pink color. And then there are two measurements made by MCE. One is the electrophoretic mobility, that's in yellow. The other one is steady state. You can see that those two values are within the uncertainty of one another. We can also measure the charge on these from capillary electrophoresis. You can see you get slightly different values, but they're all within the uncertainty of the measurements by membrane-confined electrophoresis and steady-state electrophoresis. And then you have the two electrophoretic light scattering measurements, and you get the same value, but the precision is on the order of plus or minus 25%. It's very tough to trust numbers coming off these instruments right now, even though we do use them in our lab every once in a while. Now, the membrane-confined electrophoresis provides two ways of getting the charge. The first one is electrophoretic mobility, where we monitor a boundary as it moves down the cell, and the ratio of the velocity to the electric field gives us electrophoretic mobility. It provides some sample fractionation, so the data shown to the right for soybean trypsin inhibitor, and this sample has about 10% dimer in it. You can see that we can fit those data to two boundaries. One is the monomer, has a charge of about -8, and the other one is about -7, and the other one is corresponds to the dimer and has a charge near -14. And it takes about 20 minutes to complete one of these experiments. The steady state electrophoresis removes the hydrodynamics, and the reason it is so much more accurate is under these conditions, the protein does not contribute to the current, to the electrical current, because it is effectively not moving in here. And so it's a first principle method. The exponent of the data to the right gives you the effective charge directly. There's no frictional coefficient involved in these measurements. And the inset shows you the fitting, the uncertainty in terms of 5,000ths of an OD variation as you fit these two exponents. Pull out the exponent to different electric fields. When you do so, you can combine these data and get a very accurate determination of the charge.